Welcome to Chapter 8, Section 4. This is the last section of Chapter 8. And so we're finishing off our hypothesis testing for two samples, just dealing with proportions this time. So before we start, our first step anytime we do our hypothesis testing is check our conditions. So there are three. The first two are the same as what we've always been doing. We want our samples to be random. We want our samples to be independent. Remember, independent samples is where the two groups of people are not the same people or same objects. And then the third one is similar to what we've done before. It was n times p has to be greater than 5, n times q has to be greater than 5. But now because we have two samples, we have two different sets to check. There's also this thing with a p with a line on top, like p bar. The way to find it is through these formulas here, and I'll show you how to use them once we have some numbers to work with. This is going to be your test statistic formula. And again, I'll show you how to use it once we have some numbers. So here we go. Let's do an example. So in this example, we have a study of 150 randomly selected occupants. Okay, so that's important. In passenger cars, and then 200 randomly selected occupants in pickup trucks. Okay, so this is clearly two different samples of different people because we got some people in passenger cars, some people in pickup trucks. And then our P, remember P stands for percent. So here we're given the percent of 86. And then another percent for the pickup trucks for 74%. Okay, at alpha equals 0.10, can you reject the claim that the proportion of occupants who wear seatbelts is the same for passenger cars and trucks? Okay. So I'm just going to start labeling the different variables that I have so far. So in our problem, the numbers that we were given, we have one sample size of 150, another sample size of 200. So that'll be our N1, N2. And then remember percents. This is our P hat 1 and P hat 2 here. So P with the hat on top is our percents that we're talking about in our problems. Okay. In order to use our formulas for all of our conditions, we need to check for or look for P bar and Q bar. So P bar is going to be x1 plus x2 over n1 plus n2. So we have n1 and n2. They gave us those numbers here. x1 and x2 stand for the actual number of people or of objects based on the percents. So it's not a percent, the x1, x2, it's actually a number. To find x1 and x2, you're going to take your n1, your sample size, and multiply it by the percent for that sample. And then you're going to do the same thing for the second sample to find x1 and x2. So for this problem, x1 for us is going to be 150 because that was our n1 times our first percent, which was 0.86. So that'll be x1. And then we're going to add that to n2, which was 200 times our percent for the second sample, which was 0.74. And then we end up dividing by n1 plus n2. When I do that, I end up getting 0.791. To find Q bar, it's going to be 1 minus what the number I just got, which is going to be 0.209. Okay, so checking our conditions, we have randomly selected groups because they gave that to us in the problem. There are two different groups of people, and then then we have to check our n1 times p, n1 times q, n2 times p, and 2 times q. I kind of ran out of space, so I'm just going to do this out onto another piece of paper so you can see it all. But we're doing n1 times p, so n1 for us was 150 times the 0.791 that we got from our p bar. N1 times q would be the 150 times the 0.209 that we got before. And then we're going to do the same things with our n2, which was 200. So when you multiply this all out, you get 118.65, 31.35, 158.2, 41.8. So we're checking that all of these numbers are greater than 5, and they are, obviously. So that means we can continue with our problem. So for our hypotheses, when we write our HOHA, this time because we have proportions instead of means, we're dealing with percents. So it'll be P1 and P2 instead of mu1, mu2. Okay, in this problem, it's asking that, can you reject the claim that the proportion of occupants who wear seatbelts is the same for passenger cars and trucks? If it's the same, that means they're equal. So equal signs go in HO. So that means our HA has to be does not equal. Alpha they gave us was 0.10 in this problem. So let's do our test statistics. So we're following this formula right here. So it is a z-score. So again, z-scores mean that we are in our pink chart. So have that out, get that ready. But our z-score is going to be, on top we have P1 hat minus P2 hat. These are your percents that were given in the problem. The thing with the hat on top is the percents. The one with a line on top, that's what we found when we did this craziness. Okay, so our percents. Again, make sure you turn them into decimals. So we have 0.86 minus 0.74, because those were the percents that we were given. Then on the bottom, we have our giant square root. We have the 0.791 times the 0.209 from the P times Q. And then we multiply that by 1 over N1, which is 150, plus 1 over N2. Okay, I'm just going to do this step by step in the calculator. So I'm going to do everything on top first to get 0.12 from subtracting 0.86 and 0.74. On the bottom, when you do just the stuff on the inside, multiplying these two numbers times all of this stuff, you should get like 0.001928 something. I'm not going to round anything off yet. I'm going to keep all the decimals in my calculator as long as I can. And then when I square root this bottom number, I end up with 0.0439 something. Again, not getting rid of any decimals until after I divide. So dividing these two numbers, I get 2.732. So that's my test statistic. So now with my rejection region, I'm going to draw out my normal curve. My HA does not equal, so this is a two-sided problem. So I'm going to shade both sides of my normal curve. And then since alpha is 0.10, if I need both sides to add up to 0.10, that means each side has to be alpha divided by 2, so I get 0.05 from each side. Okay, looking in my my pink chart here for my z-scores, I'm looking for 0.05 because that's what's on the left of the shaded region. So 0.05 looks like it's down here, so right in between these two. So that would be a z-score of negative 1.645. And remember, the negative one goes on the left, so that means the positive number has to go on the right. Okay. The test statistic that we got was 2.732, which would be on the right side because that's bigger. So that would be in the shaded region. And since it is in the shaded region, we would reject. And again, I don't need you to keep writing out your decision, so I just need to know, are you rejecting or failing to reject HO? Cool. Okay. I want to do one more example where the setup is slightly different. So in the second example, we have a medical research team conducted a test to test its effect of cholesterol-reducing medication. At the end of the study, the researchers found that 4,700 randomly selected subjects who took the medication, 301 died of heart disease. Okay, so here we come across numbers that are important. So we got 4,700 people total who took the medication, and then 301 of them died of heart disease. Then in a second sample, we have 4,300 randomly selected subjects who took a placebo. 357 died of heart disease from them. So that's our two different samples, and they didn't give us a percent. So we're trying to see, can you support the claim that the death rate due to heart disease is lower for those who took the medication than for those who took the placebo? But because we didn't get percents, we need to calculate them ourselves. But the nice thing is, if they don't give you a percent, that means this first number here in our first sample, that's your x1. So they've already given that to us. We just don't have to calculate that. We just need our percents, and that'll be x2. So to find our percent for our first sample, it'll be 301 x1 over n1. From that, we end up with 0.064, and then if we do the same thing to find our second percentage, p hat 2, it's going to be 357 over 4,300, and that comes out to be 0.083. Okay, so we still need to figure out P bar and Q bar. So x1 plus x2 would be the 301 plus 357 over n1 plus n2. So that would be the 4,700 plus 4,300. From that, we end up with 658 on top and 9,000 on the bottom. So dividing that out, we get 0.073. So for Q bar, 1 minus 0.073 is going to be 0.927. Okay, so we have randomly selected samples. We have 2 different groups of people. So these are independent samples. And then to find our N1 times P and N1 times Q, and 2 times P and 2 times Q. Okay, so multiplying out, N1 was 4,700 times P was 0.073, and then multiplying by Q is 0.927. After we multiplied that out for N1 and N2, we end up with all numbers that are greater than 5. We did it. Okay, so looking at our hypotheses, HO and HA. The claim in this problem is that the death rate is supposed to be lower for those who took the medication than for those who took the placebo. So if it's lower, that's a less than sign. So less than usually goes into HA. So if HA is less than, then HO has to be greater than or equal to. And then they told us alpha was 0.01 in this problem. Our test statistic, plugging everything in, we end up with percentages. So P1 was 0.064 and P2 was 0.083. And then big square root on the bottom, plugging in our P and Q, we have 0.073 times 0.9. Sorry guys, my memory on my phone ran out before I finished making the video and I didn't notice. So I continued and this is where I got to. So I think I finished writing the 0.927 and then I plugged in the 1 over n1 plus 1 over n2. When I typed it into my calculator, everything inside the square root, I ended up getting 0.000, a bunch of zeros, 4 of them, and then the 3 ... Square rooting that, I got 0.005 something something something, and when I finally divided everything out, I got negative 3.461. So looking at the rejection region, I have a left-sided test because it was HA was less than, so I'm shading to the left, and they told me alpha was 0.01, so this is the only shaded area I'm worrying about, so that's 0.01, same as alpha. So looking at the pink chart, 0.01 is closest to this one right here, which is negative 2.33. So our critical value is negative 2.33, but our test statistic was negative 3.461. And with 0 in the middle, negative 3.461 would be like somewhere way out here. So again, that would fall under the shaded region, so we would end up rejecting HO. Yay! That's all the examples I have. I finally fit your classwork onto one page. Very happy about that, but this is the last section of the year. Enjoy!